we're going to graph polynomials that are of degree higher than just degree 2. So we're going to leave quadratic for more complex polynomials. In a way, we have been spoiled by quadratics, and there are a lot of things that we're going to lose. So this story is more about what we don't know anymore rather than what we know. So here is what we're going to know. We know that the end behavior is large. So all we have to worry about is large positive or large negative. We're going to know the zeros, the x-intercepts, and we're going to know on what intervals is the function positive or negative. And we also know that on the entire real number line, these polynomials are always continuous and smooth. Continuous means you don't have to lift your pencil to draw the whole thing. So, for example, 1 over x is discontinuous. It has a discontinuity at 0. Polynomials don't have any kind of discontinuities. No, and smooth means there are no spikes, no sharp edges like what absolute value produces. So smooth means no spikes. This is a spike. But as long as we keep these two rules, then we are pretty close to what polynomials look like when graphed. Okay, so let us discuss what we don't know, but we used to for quadratics. What things do we lose from quadratic? In quadratics, we're used to knowing the maximum or minimum because it was the vertex. We can complete the square, use the vertex formula, and find the x and the y coordinates of maximums, minimums. And it's nice and symmetrical. We lose all that. So suppose the correct graph looks like this. This graph that I drew is also correct. In other words, we don't know the x-coordinate of this turnaround point, and we don't know the y-coordinate of this turnaround point. We intuitively detect that we have to somehow turn around, so it exists somewhere. But it's no longer symmetrical. All we know is that it's large at the end. We know where it's 0. We know where it's positive, negative. So if you look at the two graphs, whatever they share, that's the stuff that we know. And whatever they differ by, that stuff we no longer know. Okay, so let's get started graphing. Whenever we need to find out whether a product is positive or negative, we just have to figure out how many negative numbers are there in the product. So for that, we're going to have to look at the behavior of the factors with respect to positive, negative. We're not interested in anything else. Okay, we graph the line y equals x plus 5, which notice is the same as the first vector. The second one, we graph the line y equals x minus 1, and the third one is y equals x minus 3. Because we are interested in the sign positive, negative of these factors. And notice that there is no leading coefficient to complicate matters, so the leading coefficients are 1. The life of lines is pretty boring. If the slope of a line is positive, then they start out their lives negative, 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 negative. They keep going. Then there is one moment of excitement in their lives when they take a 0, and after that they're positive forever. So it's a pretty simple structure. Negative, then 0, and then positive. Same thing here. Negative, then 0, then positive. Negative, then 0, then positive. And we see where this change takes place. It's always around there 0, right? X plus 5 is negative before negative 5 and positive after. Now this picture here sort of replacing the following algebra. X plus 5 is less than 0 when x is less than negative 5, that's this part. X plus 5 is 0 when x is negative 5, that's this part. And x plus 5 is greater than 0 when x is greater than negative 5, that's in this part of the line. So this picture basically replaces this. This is the algebra to the visual that is that. So very similarly, if you look at the expression x minus 1, it's going to be negative until x becomes 1. So from negative infinity till 1, it's going to be negative. Then it takes a 0, and from then, forever, it's going to be positive. It's kind of boring, isn't it? So same thing with x minus 3, only this one moment of excitement doesn't happen at 1, it happens at 3. Okay, so this is sort of what we need to be able to graph this. Okay, so we're going to start graphing this function, By the way, this is a degree 3 function, right? If we multiply this out, we're going to get this is a quadratic, and then when we hit it with x, we're going to have a degree 3 piece. So this is a cubic or degree 3 function. So what is easy is to see that this vector is negative whenever x is less than -5 and positive when it's greater than -5. Same story here, but instead of -5, it's at 1. Same story here, but at 3. It's a little bit confusing to keep track how many factors are negative at the time. But that's just keeping track of it, so there is nothing deep or difficult going on. So let's see. We're going to start with the x-intercepts. You may notice that the distances are not to scale. So this function has 3 zeros and only these 3 zeros. That's quite important. These 3 points split the number line into 1, 2, 3, 4 parts. And inside each interval, none of the factors change behavior. They all remain the same, right? Because the only change in the first factor's life is here. For the second factor, the only change happens here. For the third factor, the only change happens at 3. So between 1 and 3, nothing interesting will ever happen. Okay, so this here is the interval from -infinity till -5. This is between -5 and 1. This is between 1 and 3. And finally, this is 3 infinity. So we made a table. Okay, so we're going to easily fill out this table row by row, and then we're going to harvest the fruit of our labor column by column. So let's see. The first factor is x plus 5. Now x plus 5 takes a 0 at -5, right? There is the 0. And it's negative before, and it's positive after. Why am I drawing 3 plus signs here? These breaks are for the other lines. It's basically negative before, positive after. If there were other fields here, it would be just plus, plus, plus. Okay, what about the next factor, x minus 1? Well, x minus 1 has its big moment of excitement at x equals 1. It's negative before, it's positive after. And finally, x minus 3 is having its big moment at x equals 3. It's negative before and positive after. You're going to get this nice diagonal shape if you organize your intercepts left to right, which I did here. Okay, so now we're going to figure out the sign of the product. On the first interval, we are multiplying 3 negative numbers. That's a negative product. So the product is negative on the left of -5. The next interval, we have 1 positive and 2 negatives, so the product of a positive and 2 negative numbers is positive. Next up, we have 1 negative, so the product is negative, and finally we're multiplying 3 positive numbers, no negative, so the product is positive. And that's pretty much all we know. So based on our table, we know that before -5, the function is negative because it's polynomial, and remember we knew that the end behavior is large. So that means that the polynomial comes into the picture like this. And then from the left of -5 to the right of -5, this function changes sign from negative to positive. So we're just going to go through like this. We're trying to create no discontinuity and no spike. And then the next 0 is going to happen at 1, where we're going to change sign from positive to negative. So we're just going to navigate as best as we can to turn around and hit 1 as a 0. And then at 3, there is a change from negative to positive, and we know that at the end, the function is large. And so this is the graph. So really, all we know whether it's positive or negative. So again, this graph would be just as correct. To figure out where this turnaround point is, we're going to have to develop techniques within calculus. So the graph does not have to indicate that. Just try to keep these rules. We know the end behavior is large, so we're not going to level out here. We know the zeros. Furthermore, we know where the function is positive or negative. And we know that the graph is continuous and smooth. So that's it. Now that we graphed our polynomial, I'm going to show you one more trick. The table is really not a method of computation. It's just a method of organization, how we keep our information organized. Unless the degrees are too high, we can actually just do it visually. So what we're going to do is we're going to graph these three in the same coordinate system, and then we're going to count the negative and positive signs on the graph. So we have y equals x plus 5 is 0 at -5, negative before, positive after. And notice by the way that if the slope was 2 or 1/2, this behavior would not be modified. If we are only interested in positive negative, then the steepness is not important. In other words, it's only the slope sign that matters, not its absolute value. Then the second factor is y equals x minus 1, which has its moment of excitement at x equals 1, negative before, positive after. Finally, x minus 3. So instead of the table, we're just going to look at this strange little graph. If we pick a point on the left of -3, we are multiplying three negative numbers, right? So the product is going to be negative here. If we pick a point here, and 0 would be convenient, we have one positive and two negative numbers. The product of such three numbers is positive. So it's kind of strange because we have to look vertically, even though I think the colors sort of tempt us to look and separate things horizontally. If it helps more, you can just, here is the positive, negative, negative. And then between 1 and 3, if you pick a point in the interval, there is one negative and two positive numbers that we're multiplying. And so the product is negative. We have to have the lines representing longer because this line is kind of missing. If we pick a point here, then this is a positive number, this is a positive number, and so is this. It's off the picture. So after 3, we have three positive numbers multiplying each other. Therefore, the product is positive. If the degree is not too high, you may not even need a table. You can just grab the three things in one coordinate system and just count. It's all about how many negatives, how many positives, given that each factor has a very simple behavior sign-wise. Thank you for watching.